In part one of this subsection, trusses, we determined the loads on the bridge support and these three zigzags, these two bottom flanges and this top flange of our weightless bridge, which has 100 pounds hanging from its center. This zigzag is in 70.7 pounds of compression, or 50 times the square root of 2 pounds of compression. This one's in 50 pounds of tension, 70.7 pounds of tension, 70.7 pounds of compression, 100 pounds of compression, 150 pounds of tension. Let's now look at this point. Here it is. Okay, it has 100 pounds of compression pushing that point to the right. It has 70.7 pounds of compression pushing that point at that 45-degree angle. So we could just erase this 70.7 pounds of compression at that direction, and we can replace it with its vertical and its horizontal components of 50 pounds each. Okay, so we have 100 pushing it to the right, 50 pushing it to the right, 50 pushing it up, and an unknown there and an unknown there. Well, this unknown, one thing we do know about this unknown is that it has no vertical component. So the vertical component of this zigzag must balance out with the vertical component here of this compression member. If this compression member is pushing up 50 pounds, this one has to have a vertical component of 50 pounds down. So it is pulling 70.7 pounds at a 45-degree angle. So let's go ahead and write that in. 70.7 tension. Tension because it's pulling this point this way. Okay, so 70.7 pounds this way is the same as 50 down. So let's go ahead and erase this. Let's write 50 down and 50 over to the right. So all the known forces on this point so far are a 50 up and a 50 down that balance, a 50 to the right, a 100 to the right, and another 50 to the right. So this top flange must be pushing this point 50 or 200 pounds, 50 plus 50 plus 100 to the left. So it would be 200 pounds of compression. So we'll go ahead and write that there. We could figure out the loads on the rest of this beam. These zigzags here, this top flange, and these two bottom flanges. But there's not really any point in it because this is a symmetric bridge. The left side looks just like the right side. So we can just go ahead and write in the numbers because it's a mirror image. We have 70.7 pounds of tension there. We'll have the same here. We have 100 pounds of compression there. We'll have the same here. Okay, this zigzag will be the same as the one to our far left, 70.7 compression. This next one will be like our zigzag there, 70.7 tension, and then 70.7 compression. This will be like the one on the left end, 50 pounds of tension, and 150 pounds of tension there. The left side looks just like the right side. Okay, there's a way we can check our answers here. Let's say we were to cut this top flange with a saw. Of course it would bind on the saw because this is a compression member. It would squeeze the saw before the saw got through cutting it. But let's just go ahead and draw us a little cut there. And let's figure out the load in this member. Let's look at all the forces acting on this beam to the left of this point. Okay, we have this 50-pound bridge support pushing up, and and its moment arm is that distance from there to there. Well, this is a 45-degree right triangle. That's a right angle. Go ahead and draw that. These are 45s, there and there. So this distance from there to there is half of this distance from here to here, because if we drop us a dotted line, we turn this 45-degree right triangle into two smaller 45-degree right triangles, with this leg of this triangle being equal to this leg and equal to this leg. So that distance is half of this distance. So this 50 times this distance must be twice as much force times half the distance, or 100 pounds of compression, because this 50 is trying to turn this clockwise about this point right here. So this compression member must try to force this part of the bridge counterclockwise about this point, which puts it in 100 pounds of compression. We could look at the forces on the other end of this bridge at this same point about here. Let's draw this point right up here. Okay, we know this distance. We have our 100 pounds of weight hanging from it. Okay, there's our flange here that's broken. We're going to ignore the left part. We've already looked at it, and we've determined that this member is in 100 pounds of compression. So let's look at what we have down here. Okay. There we go. We have our 50 pounds going up here. Okay, so let's look at all the moments about this point. We have 100 pounds times this distance. Let's call it, well, let's say this beam is h high. Call it little h from there to there. Well, we know that if that's h, this is 2h from there to there, because that's equal to that. We just turn that 90-degree, or that 45-degree right triangle, into two little 45-degree right triangles. And that is half of that. So we have 100 pounds times 2h. That would be the distance between our point and where our weight is hanging from the middle of the bridge. That 100 pounds is trying to pull this bridge clockwise. So 100 times 2h clockwise. Okay, and over here we have 50 times 246h. 50 times 6h. But it's trying to turn it counterclockwise. So 100 times 2h would be 200h. Ooh, better get a little more room here. 200h. 50 times 6h would be 300h. So we need a force in this segment right here, which is equal to 100h. Well, its distance from here to there is h, or need a bending moment of 100h. A force of 100 pounds times a distance of h will suffice. So there we go. We come up with the same answer, 100 pounds of compression for that member. That one right there. No matter which side of the bridge we look at, we imagine a member that is either above or below whatever point we're looking at. We imagine it to be broken, and we figure out what all the moments acting about this point are, and they have to equal out. It's like two people with a wrench here. Let's say here's a nut, and not a very good one. Let's say we have a wrench here, Okay. And one guy's trying to turn it this way, and he's pulling with his hand right here. There's his fingers. But another guy, he doesn't want it to go that way. He wants it to go this way, so he's pushing here, halfway between there and there. Well, this guy has to push twice as hard as this guy does because he only has half the distance compared to that. Same concept.